Welcome to The Explainer. Today, we're going to break down one of the most fundamental data structures in all of programming, the linked list. If you've ever found yourself thinking that arrays feel a bit rigid, well, you are in exactly the right place. So here's our game plan. First, we'll talk about why arrays sometimes just don't cut it. Then, we'll introduce our hero for the day, the linked list, and see how it's actually built. After that, we'll get our hands dirty with the core operations, and we'll wrap it all up with some pro-level tips on performance and common pitfalls. Okay, let's get right into it. To really appreciate why the linked list is so clever, you first have to feel the pain of what came before it. And that, of course, is the good old array. So why even bother with anything else? Arrays are fast for grabbing elements if you know their position, right? But have you ever tried to insert something into the middle of a big array? It's a real headache. They can be shockingly inflexible when your data needs to change. And this slide right here, this lays it all out. The core issue with an array is that its size is set in stone. If you want to squeeze a new element in, you literally have to shuffle every single element after it to make room. Same thing for deleting. We need something that's built for change. All right, now that we're clear on the problem, let's bring in the solution, the linked list. This is a totally different way of thinking about how data can live together in a sequence. At its heart, the idea is so simple. Think of it as a treasure hunt. Instead of one big treasure chest, you have a series of smaller boxes. Each box has some treasure inside, your data, and most importantly, a clue that tells you where to find the next box. That's it. And here's what that looks like. You've got a box with the number 10, and it holds a pointer, an arrow, that points to the box with 20. And that box points to the one with 30. This simple chain is what gives the linked list all of its power. So the concept is cool, right? A chain of boxes. But how do we actually, build one in our code? Well, it all starts with that one single building block. That building block is called a node, and every node in the entire list has just two jobs. Job 1, hold on to its own piece of data. Job 2, know the address of the very next node in the sequence. That's the whole shebang. Now, in C++, this idea translates into this beautifully simple struct. You've got a variable for your data, in this case an int, and then you have a pointer called next. And what does it point to? Another node. It's a pointer to its own kind. That little bit of magic is the link in our chain. This visual shows the biggest mind-bending difference. An array demands that all its elements live side by side in one big, unbroken block of memory. They're neighbors. But linked list nodes, they can be scattered all over your computer's memory, connected only by those crucial next pointers. And here's the most elegant part. To keep track of this entire chain, no matter if it has 3 nodes or 3 million, we only need to store one piece of information, the address of the very first node. We call this the head pointer. If you know where the chain starts, you can find everything else. Okay, we've got the blueprint, we know what a node is, we know about the head pointer. Now, let's actually make this thing do something. Let's talk about the operations that bring it to life. First up, how do you even read what's in the list? It's called traversal. You just start at the head, and you hop from one node to the next using its next pointer. You read the data, hop. Read the data, hop. You just keep doing that until you hit a pointer that's null, which is the universal sign for the end of the line. Now we get to the linked list's absolute superpower, adding a new element to the front. This is an O of 1 operation, which is just a fancy way of saying it's always fast. It takes the same tiny amount of time whether your list has 5 elements or 5 million. It's incredible. And the process is so simple, it's almost beautiful. You just create your new node, then you tell it, hey, your next pointer should point to whatever the current head of the list is, and then for the final step, you just say, guess what? You're the new head now. That's it. A quick little 3-step pointer shuffle, and you're done. Deleting is also super efficient, but it comes with a golden rule. You have to rewire the chain first to skip over the node you want to delete. If you free the memory before you fix the pointers, you've broken the chain, and the rest of your list is just gone, lost in memory forever. So to delete from the front, it's simple. You just update the main head pointer to point to the second node in the list. This basically cuts the old first node out of the chain. Then, and only then, after it's been safely disconnected, do you delete it and free up its memory.
All right, we've got the mechanics down, but moving from just knowing how it works to truly mastering it means understanding the trade-offs, the common mistakes, and of course, the modern C++ way of doing things.
Working with raw pointers is powerful, but you gotta be careful. These are the classic traps everyone falls into. Forgetting to delete causes memory leaks, messing up the head pointer orphans your whole list. It's easy to do, so you have to stay sharp. But here's the good news. Modern C++ gives us this amazing tool called a smart pointer. If you use something like std unique pointer for your next pointer, it's like hiring an automatic cleanup crew. It handles all the memory management for you so you can't forget to delete anything. It's so much safer. And this table right here really tells the whole story. You get that incredible lightning-fast O1 performance for insertions at the front. But here's the trade-off. If you want to get to the 500th element, you have to start at the head and hop 499 times to get there. That's what ON means. The time it takes grows in a straight line with the size of the list. So what's the big takeaway? There is no best data structure. It's all about picking the right tool for the specific job you're doing. If your program is all about adding and removing things constantly, especially at the beginning, a linked list is your best friend. But if you need to instantly jump to any element, or if you need every last ounce of cache performance, an array is probably the better call. And that's what's so cool. Now that you get the fundamentals, you can start to really understand the design choices behind the professional-grade libraries. So I'll leave you with a question to think about. Now that you can build this, what else would it need to be ready for the real world? Maybe a way to go backwards. That's your next step on the journey.